Now, let's continue with the implication of that. What if I'm dealing with an isolated system? What does that mean? It means the system does not exchange heat with the environment. Okay, I isolate it from the rest. Okay, stuff can go on inside, but it does not exchange heat with the outside. So dq is equal to 0, right? Now remember, dq equals, then look at this quantity dq over t. Remember, dq equal to 0, so dq over t is also equal to 0. Okay, now remember, dq over t equals ds if it's a reversible process. But dq over t is also equal to 0, which means ds equals 0 if this isolated system undergoes a reversible process. Okay, undergoes a reversible process. And in the case of irreversible process, this quantity is equal to 0 because dq is equal to 0. Yet, at the same time, ds is greater than that for irreversible process, remember? But this quantity is equal to 0, which means delta s is greater than 0. Okay, because it's greater than this quantity, which is equal to 0. That's what happens in an irreversible process. Okay, all real processes are irreversible. But you look at an ideal case when it actually can be reversible, it turns out for an isolated system, delta S equals 0. But if it's an irreversible process, such as in real life, delta S is greater than 0. But in either case, you find delta S is never negative, which means entropy can only increase for an isolated system. Okay, isolated system. S never decreases for any isolated system. So finally, we have some idea how to find the correct direction of the arrow of time. How come certain things never happen forward? Or, how come certain things can never happen backward, can only happen forward? In other words, it is never reversible. Well, simple. We just have to look at whether the quantity S increases or decreases. By the way, as you definitely have guessed, the quantity S is called entropy. Okay, entropy. This quantity, entropy, for an isolated system, turns out, due to our analysis, it can never decrease. In fact, if the process is reversible, then the entropy stays the same. And if the process is irreversible, then S becomes greater and greater and greater. So this tells us how to point the correct arrow of time. Just look at how the entropy S changes. If the entropy does not change, we say, yeah, this thing is reversible. Okay, it can go both forward and backward. And if the entropy increases, then we say, okay, this process is irreversible because delta S is greater than 0 for any irreversible process of an isolated system. Okay, now when I say an isolated system, what exactly does it mean? Well, it means it does not exchange heat with the environment. Okay, for example, if you have a cup of water, okay, if you have a cup of water, it's hotter than the surrounding. Now, if you leave it alone, okay, you leave it alone, of course, it's going to absorb, it's going to lose some heat, right? It's going to lose some heat, so its entropy is going to change. So for this process, the water alone is not an isolated system because it does change heat. It actually loses heat to the environment. So in this sense, we're not dealing with an isolated system for water alone. And as a matter of fact, as heat leaves water, the entropy of water actually decreases. Right? The entropy of water decreases. This does not violate what we just said, because we said entropy can never decrease, because that was a condition that it must be an isolated system. Okay, this water exchanges heat with the environment. It is not an isolated system. How do you make an isolated system? Well, we can think of water and the surrounding air as one single system. Right? Now, if that is the case, then we say water plus the air around it, that in fact is an isolated system because heat does not leave that system. Okay, it only goes from water, which is part of the system, to the air, which is another part of the same system. All right, there isn't a heat exchange between different parts of the system, but the system alone, the system as a whole, water plus the air around it, is in fact isolated. Okay, so we can declare that for that system, which is water plus the air around it, the entropy can never decrease because it is an isolated system. Okay, now, how do we show that the cooling down of water is actually an irreversible process? We know it's irreversible, right? So we have a cup of water, right? we have a cup of water, and it's hot. Okay, it's hot to begin with. And then, so this is the beginning, right? This is the immediate. This is the initial stage. And of course, you got some air around it. The air is initially the air is kind of cold. Now, here's the final stage. Here's the final stage. When the water cools down a bit, okay, the water cools down a bit, and the air gets a little bit warmer. Okay, the air gets a little bit warmer, so that's the final stage. So heat has left the water and gets absorbed by the air. If you treat water and air as a single system, that is isolated because, you know, heat never actually leaves the system, only goes from water to air, which are both part of the system. How do you show this is irreversible? Well, simple. All I have to show is that the entropy as a whole decreases. Increases. Okay, so it's irreversible. You know, water loses heat, so its own entropy decreases. Air gains heat, so its own entropy increases. But what's the total change in entropy for both the water and the air? Let's say a certain amount of heat Q leaves water. Okay, this is the amount of heat Q. It's absolute. Let's take the absolute value. What is the change in the entropy of water? Delta S water. Well, it's negative because it loses heat. Okay, negative Q over T water. Now be careful here because the water temperature actually changes. Okay, so I'm going to have to use some sort of average value. Okay, some sort of average value. Meanwhile, the change in entropy for air, what's that equal to? Now that is positive. It gets the same amount of heat Q divided by some sort of average value of air temperature. Right? So what is the total change in entropy for the water-air system as a whole? You know, for this whole thing, going from initial to final state. Well, just have to add them up, right? So delta S for the entire system is the sum of these two. Delta S water plus delta S air. Let's see now. This plus that. Okay, I'm going to take that Q out. It's the same value. And then 1 minus. This is a positive term. Here's a minus negative term. So I'm going to take this term first. TA bar minus 1 over TW bar. The question is this positive or negative? Or is it positive, 0 or negative? I mean, it's impossible to be negative, okay? You know, because it's an isolated system, the entropy can never decrease. If it's 0, then the process is reversible. If it's positive, then it is irreversible. Okay, it's never negative. Now let's see, is it positive or is it 0? We got only two possibilities. Well, that depends on the average value of the air temperature and the average value of the water temperature. The average value of the water temperature is some sort of average temperature as the water decreases its temperature from initial value to the final value. Of course, the final value is that the air and water temperature become the same, right? So the average value of the water temperature has got to be higher than the final air temperature. Meanwhile, what happens to the air? The air actually warms up, right, from the initial temperature to the final temperature. Okay, so the average air temperature is actually lower than the final air temperature. Okay, so this is lower than the final air temperature. This is warmer than the final air temperature. That means T water average is greater than T air average. That makes sense. But you take the reciprocal, you'll find that this first term, 1 over TA, is greater than the second term, 1 over T water, and therefore this, in fact, is greater than 0. So indeed, is it reversible or irreversible? Well, delta S is greater than 0, so irreversible. So you see, not only can we judge from common sense that this process is irreversible, we can now actually use a scientific calculation to prove that this is irreversible because, after all, the quantity of entropy for the whole system increased for this isolated system. Therefore, we say this is an irreversible process. Okay, now let's look at some classic examples of how to find the entropy change. Example 1. It's what's called free expansion of an ideal gas. What's a free expansion? Well, a free expansion is when gas expands into a vacuum. Okay, it expands into a vacuum. Suppose you have a pressurized tank of gas, all right, and I remove the plug, and the pressurized air inside rushes into the air outside. Is that a free expansion? No, because it expands not into a vacuum but into the surrounding air, even though at lower pressure. Okay, it is not a free expansion. Let me give you an example of free expansion. Suppose you have a tank of gas. Okay, there's a partition here. There's a partition here, which prevents the gas from going to the other side. The other side has nothing in it. It's just vacuum, okay, nothing in it. No, so that's the initial state, right? And all of a sudden, you take away that partition, okay? This partition is gone. So what happens? Well, before you know it, the gas is going to occupy the entire volume, right? It has expanded into vacuum. That is called free expansion. So that's the final state. What I want to know is, what is the entropy change going from this state to that state? Okay, what is delta S? And from the value of delta S, I can judge for myself whether this process is reversible or irreversible. I'm assuming that this is thermally insulated from outside, so that this indeed is an isolated system. There's no heat exchange between this tank of gas and the surrounding. Okay, how do I do that? Well, I'm going to use the formula ds equals dqr over t. On the PV diagram, here's the initial state with lower volume, and here's the final state with higher volume, of course, lower pressure. Okay, you go from here to there through free expansion. Let me ask you, is free expansion reversible? Well, common sense tells us it's not reversible, right? If it's reversible, you know, how about if you know, we start with an oxygen tank in the middle of a in the middle of a room that's devoid of any oxygen. If I pull the tank open, of course, before we know, the oxygen is going to fill the entire room, right? And you can come in and you can breathe, no problem, right? Are you going to worry about the possibility that all the oxygen molecules will suddenly find its way back into the oxygen tank so that you cannot breathe anymore? Of course, that's ridiculous. It doesn't happen, right? So this is not a reversible process. Free expansion is irreversible by common sense. Okay, so therefore, when you connect initial step and final step, you cannot use this free expansion thing. I, in fact, use broken lines because this is not... Okay, you cannot even use a solid line here because a solid line means at every point, it's got a certain volume and certain pressure and a certain temperature. This, you cannot even define the temperature in the middle going from here to there, because temperature requires thermal equilibrium. In the middle of the expansion, this thing is not in thermal equilibrium. Okay, so I cannot even use a solid line. I have to use a broken line. And even if you could use a solid line, it still doesn't work because this is not a reversible process. Remember, if I want to use ds equals dq over t, this s, this dq must be in a reversible process. So you see, I must devise a reversible process to connect initial and final so that I can use this formula. Now remember, S is a function of state. Okay, it depends on initial and final value. So delta S only depends on initial state and final state. It has nothing to do with how you go from here to there. It only cares where you start with, where you end up with. It has nothing to do with how you get there. But for us to calculate delta S, we must imagine a reversible process going from here to there, and then we can use that formula to do the calculation. Okay, so the question is, what kind of reversible process can we devise that connects between these two? Let's see now. This is an ideal gas. Okay, an ideal gas, and you look at what happens between here and there. The gas expands into a vacuum. When the gas expands into a vacuum, does it have to push around? No. Because you just remove the partition, the gas molecule, instead of bouncing back, it just keeps on going, right? And when it keeps on going, does it lose any kinetic energy? Not really. Okay, so the gas molecules, because the remove of the partition, it keeps on going, it doesn't do any work or anything to push things around. Therefore, it does not lose any energy. And so on average, the temperature does not change because the gas did not lose any energy. Okay, the temperature does not change. What does that tell you? It means there is no change in internal energy. The free expansion leaves the energy as a constant. And since for ideal gas, the internal energy is proportional to temperature, we find that once you settle down from initial to final, once the final state has been reached, the final temperature equal the initial temperature. Okay, they're equal. The temperatures are equal. And what that means is that even though the real process of free expansion going from here to there is not isothermal, there exists a line which joins these 2 points and is an isothermal line. Because after all, they have the same temperature. Okay, the real process is not isothermal, but I can actually go from here to there. I can reach from initial to final state through an isothermal line. Okay, so that's the concept. Ti equals Tf is an ideal gas. Okay, the reason why Ti equals Tf again is because Ei equals Ef. There is no change in internal energy, and therefore there is no change in temperature. So why not take an isothermal path going from initial to final? Because, after all, the isothermal path, unlike the free expansion, is reversible. Okay, please note again that the actual expansion is not isothermal, and it's not reversible. I am using an artificial path to connect initial and final, and that artificial path is isothermal and it's reversible. Since it is reversible, I can use that path to calculate delta S. Okay, so dQr, R is reversible, equals negative dW equals PdV. Why is that? Because all the work, all the heat you absorb is being used to do work. Okay, the work done on the gas is dW, the work done by the gas is negative dW. Takes all the heat to do work, leaving nothing to change the energy of the system. And that equals, of course, PdV. Okay, so ds equals dQr over T, that's PdV over T. Okay, the rest is simple. All you have to do is to integrate both sides. Of course, there is a T is a constant, but there is a P that changes. I want to replace P in terms of V and T. So that's simple. P equals nRT. Okay, so P equals nRT over V, which are plugging, right? So it's nRT over V, right? nRT over V, that's P. And you cross out these two T's, you get nRdV over V, going from V initial to V final. That is a natural log function, right? dV over V. So what's the answer? It's n times r times log of V final over V initial. That is the answer. The entropy change in a free expansion. All right, take a good look at the result. nr log V final over V initial. You see, mathematically, if V final is greater than V initial, then the log function, the argument is greater than 1, which means the log function is positive, okay, if V final is V initial. But if V final is less than V initial, what does that tell you? The log function has an argument that's less than 1, therefore the log function is negative, the delta S is less than 0. Okay, which one is possible? Well, in a free expansion, the gas actually increases volume, right? So this is the possible case when delta S is greater than 0. And to have V final less than V initial, that means the gas automatically shrinks. We know that doesn't happen, right? Doesn't happen. And then we can understand why does it doesn't happen from the point of view of entropy, because that will leave entropy change as a negative value for an isolated system. We know that doesn't happen. Okay, the entropy for an isolated system can never decrease. So that's why we say V final is never less than V initial. Okay, it also tells us that free expansion, in which you have a smaller final volume, a small initial volume expanding to a greater final volume, free expansion, is an irreversible process. Not only is that process possible, but it is actually irreversible. You can never go back. Why? Because delta S is not equal to 0, but rather is greater than 0. Okay? Remember, once again, for an isolated system, if a process leaves the entropy increased, it must be irreversible. Okay? If it leaves the entropy unchanged, then it's reversible. But in our case, delta S is greater than 0, so now we can understand why. Okay, scientifically, not just through experience, that the free expansion is indeed irreversible. Okay, another example is the mixture of water at different temperatures. Suppose I have a tank of water and another tank of water. They're identical, they have the same mass and everything, except that they don't have the same temperature. T1 colder than T2. Okay, you mix them together. You don't, let's assume that heat does not get lost into the air or whatever. Everything is done in isolated manner, so that these two tanks of water forms a system that's isolated. Okay, you mix them together, they have the same exact mass, so that the final temperature is half of T initial, of T1 and T2, right? Let's look at the change in entropy for these two tanks of water in our process. This guy is going to absorb some heat, so its temperature is going to rise. And its entropy is also going to rise. This guy is going to lose some heat, so its temperature drops, and so does its entropy. But what I want to know is, as you mix these two, what is the total change in entropy? And if that total change is a positive number, that means this mixing process will never be reversed, cannot be reversed. And if the total change in entropy is equal to 0, that means it's going to reverse itself. Now we know that doesn't happen, right? If you mix hot and cold water, once you mix it, you get lukewarm water, and that's it. You cannot separate hot and cold anymore automatically. So we hope that delta S will be greater than 0. Okay, is this really the case? Okay, let's take a look. For the colder water, dq1 equals Cm dt1, right? And so during the time, temperature change dt1, this is dq1. Of course, it has to be a reversible process. How do you make it reversible? The idea is that in a real mixing, things happen so fast, it's always irreversible. But what I'm going to do is I'm going to change the temperature ever so slowly. Okay, give it a tiny, tiny, tiny temperature change. Well, since the temperature change is so tiny, you can imagine it won't be that difficult to imagine that it can be reversible, because if the temperature, say, changes by 1/1000th of a degree, increases, if you decrease by 1/1000th of a degree, it's not a big deal, right? So that's how I make the process reversible, making it, imagine a very, very, very slow process, not the actual mixing, which takes place too fast. Okay, so there's a dt1, it's tiny, tiny temperature change. During that interval, what is the change in entropy for this water? That would be dq1 over T1, right? Over the temperature at that moment. Okay, so ds1 is equal to Cm dt1 over T1. Okay, I'm going to integrate that to get net change in entropy for 1 tank of water. Okay, I'm going to assume first this is the cold water, so that its final temperature is greater than initial temperature. So you have T1 over to T final. T final is, as you know, 1/2 of T initial plus T final, 1/2 of T1 plus T2. Let's see what is that equal to. Okay, this is Cm natural log, right? dt over T natural log, so log of T final over T1. Okay, T initial is just equal to T1 for the cold one. Next, let's look at the second one. This is the hot water. It cools down, so its ds is actually negative. Okay, so this is delta S1, right? And similarly, delta S2. I can do a similar calculation and find same mass, okay? Log of, what happens for that guy? Well, you have T final over T2. Right? T2 is greater than T final, so this log function is argument less than 1, so delta S2 is actually negative. The hot water lost heat, therefore it also lost entropy. But that's okay, let's add them together. Okay, it's the total change entropy that I'm interested. So what is the total change entropy? Delta S for the entire system equals delta S1 plus delta S2. Let's do this calculation, shall we? Cm, okay, that's a constant, I'm going to take that out. Okay, so you have log this plus log that, right? Tf over T1 plus log Tf over T2. Now, we're curious. We want to know whether this quantity is positive or negative. Okay? The sum of the two log functions. Let's do that. Let's find that out. Okay, that's Cm. You know, log A plus log B is log of AB, right? So that's log of Tf squared over T1, T2. Is this positive or is this negative? Well, that depends on whether this argument of the log function is greater or less than 1. Okay? If it's greater than 1, of course, delta S is positive. Okay, now let's see now. What's Tf anyway? Tf is half of T1 and T2, right? Half of T1 plus T2. So Tf equals 1/2 T1 plus T2. So let's see now. Let us now find this ratio, Tf squared over T1, T2. Let's see what that is equal to, okay? That will be equal to, Tf is equal to this, right? So I'm going to square it, right? So it's T1 plus T2, right? Squared divided by 4. Okay, so I have to square it. 4 T1, T2. Now, is this greater than 1, equal to 1, or less than 1? Well, I'm going to show you. This definitely is greater than 1. How do I know that? Because after all, you work this out, okay? What is that? That's T1 squared plus 2T1 T2 plus T2 squared, right? So this is just to say that T1 squared plus 2T1 T2 plus T2 squared has to be greater than 4T1 T2, right? This is numerator, this is the denominator, right? I want to show that the numerator is greater than the denominator so that the ratio is greater than 1. Now, is this obvious? Yeah, this is obvious because you cancel out 2T1 T2. Okay, there's 2T1 T2, so you cross that out, that becomes 2T1 T2. And you move that one to the other side, this actually just becomes negative, and this becomes 0. Right? This becomes 0. But that is guaranteed because this really is just T1 minus T2 squared. That is guaranteed to be greater than 0, no matter what T1, T2 are. They've got to be greater than 0 unless T1 is equal to T2. Of course, when T1 is equal to T2, nothing is going on, okay? You didn't do anything because the two temperatures being the same, you don't mix anything, okay? There's no change, of course, that's irrelevant. So as long as T1 and T2 are different, you'll find that this ratio here is always greater than 1, and therefore the log function is always positive, and delta S is always greater than 0, which means this process indeed is irreversible. So you see, once again, with the concept of entropy, we can actually do this calculation, and using calculation, we don't have to rely on common sense anymore. We can figure out quantitatively that this process is indeed irreversible because the change in entropy is positive.